Engineering Mechanistatics Lecture 19. So this is chapter 4, which is Center of Gravity and Centroid. So we're gonna go for the first part, which is Introduction, and then the second one, Center of Gravity or Center of Mass for a system of particles, and Center of Gravity or Center of Mass and Centroid for a body. The objective is to understand the concept of center of gravity, center of mass, and centroid. Okay, this is the application. If let's say if we want to design a structure to support the tank here, okay, so the structure is like this. So we want to know the force coming from the tank, okay. So but the tank has the water inside, so of course the water will give the distributed load, okay. So if it is have a distributed load like this, so how we want to do the analysis for the structure? So simply we can represent the distributed load with one resultant force Fr here. So okay, like the one we already learned previously. So this represent of force resultant here, so we need to calculate, and then the location of the resultant force we need to determine. So let's recall back the way how we want to calculate the F resultants for the distributed load. If you still remember, I already explained in lecture 12, so please watch this lecture first if you want to go through for this lecture, for this present lecture, which is lecture 19. Okay, so how we want to calculate the force resultant here? Okay, you need to do the integration of differential of force here. Differential means from F here to F here with the function of the distance, which means that from the first distance x to the certain distance here. Okay, so this one we call it as differential of the x, and then when you do the integration of df, you will get the area under the curve. So the area under the curve is the amount of the f resultant. Okay, and then if let's say we can represent the f resultant that we already calculate using this equation, become like this. Okay, so let's say we have an fr somewhere here, and then we have a line of action here from O to the fr. So this line of action we denote it as x bar. So this way it will produce a moment about the point O, where the MO or M resultant about point O is equals to line of action x bar multiply with Fr. Okay, so like this one. Okay, so we can rearrange the equation to find the x bar. What is an x bar here? So x bar is equals to mr over fr. Okay, so substitute your mr with these equations, and then your fr previously with this one. Okay, so you will find you will get the formula for the x bar is equal to this one. Okay, or simply is the integration of x, the differential of area over the integration of diffusion of area. Okay. Another important thing that I like to highlight here is if you see here, this one is equals to this one, right? So which means that m is equals to integration of x dA. So this one we call it as a first moment of area with respect to a y-axis. Okay. So if the value here is x, is the function here is x, so this we call it as a first moment with respect to y-axis. If the function here is y or y dA, so we call it as a moment, the first moment with respect to x-axis. Okay, so please remember that. So if we can summarize, it will become like this lah. Okay, so the first moment of the area with respect to y-axis, if this one, okay, so and then we denote it, the first moment with the symbol of qy, and then the first moment of area with respect to x-axis is this one, and then we denote it as qx.